Are there any people coming today? If we reschedule, when will the class be? Okay, I'll just do the recording then. Because there won't be any discussion time, right? Because there's no students. So it'll be faster. Okay, okay. Is this still recording? Oh, okay. Welcome to Mine and Z Junior Combinatorics. Today we'll be covering invariants. So first, we'll cover a warm-up section. After that, we'll do some introduction problems and concepts. And also we'll cover some common invariants in Math Olympiad. And finally, we'll go over applying these invariants in our handout problems. So our warm-up will consist of two problems. In the first problem, we have two piles of coins. One has 7 coins and the other has 5. Alan moves one coin from one pile to the other. How many coins in total do we have? So in this scenario, it's pretty straightforward. We have an initial state where where one pile has 7 coins and the other has 5. And then we have an action being performed where I move one coin from one pile to the other, and the total number of coins will stay the same. So we can call that an invariant because the total number stays the same after performing an action. And in the second problem, we take any odd number. If we keep adding 2, will we ever get an even number? So obviously, if we take 2n plus 1 and we add 2 some number of times, we'll get 2k plus 1, which is still an odd number. So the property of being odd doesn't change after performing some steps, which means that our invariant is the parity or odd and evenness. So here we have an example problem. We have 100 coins on a table. Some show heads and others show tails. If we flip 2 coins that show the same side each turn, with what initial conditions can we reach all heads or all tails? So whenever we see something changing by 2 or by an even number each time, we should probably recognize even and oddness or just parity. And if we start off with, say, an even number of coins showing heads, then we have an even number of coins showing tails, as the number 100 is even, right? We can write that as 2k heads and 100 minus 2k equals 50, or equals, 2 times 50 minus k. And 50 minus k is a whole number, so 2 times 50 minus k is an even number as well. And then we can just flip these coins showing tails each time to get all heads, or we can flip these 2k coins showing heads by flipping 2 coins each time. And then in the end, after some number of moves, we'll have 100 coins all showing heads or all showing tails. But on the other hand, if we start off with 2k plus 1 heads, then we have 100 minus 2k plus 1 tails, which is equal to 99 minus 2k tails. And this is an odd number minus an even number, and we know that odd minus even is also odd, right? So every time, so we have an odd number of heads and an odd number of tails. And then each time we can change it by 2. We can change the number of heads by 2, or we can change the number of tails by 2. So after some number of moves, we'll have, let's say we're changing heads, we'll have 2k plus 1, like plus a, where a can be positive or negative, plus 2a. And then the other one for tails, we'll have 99 minus 2k minus 2a. And then as we can see, we can just factor this into 2k plus a plus 1, which is odd, right? And then 99 minus 2 times k plus a. So we have 2 odd numbers after performing some number of moves on heads and tail coins. And this means that we will always have an odd number after some move, but then we want 100 coins to be heads or tails, and 100 is an even number. So we have a contradiction because we can only reach odd numbers starting with an odd initial state, which means we must have in initial conditions that we have an even number of heads and an even number of tails. So this is what some invariant problems will look like. Lots of them involve chessboards. This is one of the most famous invariant problems. So we remove 2 opposite corners from a board. Let's say we remove A8 and H1. And then can we still tile the chessboard with 2x1 dominoes? So that's just a taste of an invariant problem. We'll cover it later. So now I'll go over an introduction to invariants and some common invariants that will show up in Math Olympiad. So an invariant is a quantity, property, or value that remains unchanged throughout a process or transformation, even as other aspects of the problem change. So it's just something that does not change during a process, even though other things do. So we've already covered 2 scenarios where we move coins between piles, which does not change the total number of coins. And we also repeatedly added 2 to an odd number, which causes it to stay odd because it started out odd. So parity stays the same. So apart from invariants, we also have monovariants. Invariants don't change, and monovariants change only in one direction. So they either increase or decrease, up or down. So in problems involving monovariants usually ask you to return back to a state during a game or during some process. But then there's probably some property that you need to find in these problems that show that it is always increasing or decreasing. So you'll never be able to return to the same initial conditions. So the classic invariants are parity, coloring, and sum product. Parity is odd and evenness. There's also modular invariance, which is like mod 3, mod 4, mod 5. Coloring invariant is where it's usually presented in a grid, and then you can assign some colors to the grid. And then there's also sum and product invariance, where most commonly it's like you have some numbers on a blackboard or whiteboard, and then you replace two numbers each turn with one number. Or it's a game with number replacement or movement. So here's an example. You have a 6x6 grid of lights, which are initially all off. Each turn, you flip an entire row or column of lights. Can you end with exactly one light on? So, no. In this problem, we can just prove it exhaustively. So without loss of generality, we can flip both grids, both rows or columns. So let's just deal with grids. Let's just deal with rows. So one scenario is that we have 3 on and 3 off in a row. After we flip, we get 3 off and then 3 on again, right? So notice the number of lights on or off has not changed at all, which means it changes by 0. Another scenario is we have 4 on and 2 off. When we flip this, we get 2 on and 4 off, right? So this has changed by an even number, which is 2, and this also has changed by an even number, 2. And then we also have another state, which is 5 and 1 and 1 and 5, which gives us 1 and 5 or 5 and 1. And then we also have 6 and 0 and 0 and 6. This difference is 6, this difference is 6, this difference is 4, this difference is 4. So if we look closely, we get differences of 0, 2, 4, 6. When you look at these numbers closely, you realize that all of these numbers are even. So after performing any move, we can only change the number of grid lights that are on or off by an even amount, right? And since initially all of them are off, which means we have 0 are on and 36 are off, which is even, right? Then we can only end up with an even number of lights on or off after some number of moves. And when we have exactly one light on, we have 35 lights off, right? Which means that we have an odd number of lights on and an odd number of lights off, which is impossible. So no, we cannot reach the end state with exactly one light on. So some common invariants you'll see in Math Olympiad involve parity / modular arithmetic, which is just, parity is just odd or evenness or mod 2, and modular arithmetic usually extends further to like mod 3 for like mod 3, 4, 5, or 6. There's also sums or weighted sums. In sums, it's basically just, you just take the sum of every single element you're given. Well, that's in the basic case, or you can assign weighted sums. You can assign values to different elements or positions. And then there's also coloring arguments where you have to color a board or you're given a colored board. So here is a parity invariant. A knight starts on any black square of a chessboard. After an odd number of moves, can it end on another black square of the chessboard? So, when we look at a knight's possible moves on a chessboard, what do you notice? If it starts on a black square, it can only move to a white square. And if it starts on a white square, it can only move to a black square. Which means, uh, wait, yeah, so when we start on this is black, we move to a white square. When we start on white, we move to black. And initially, we start on a black square. And then we want an odd number of moves, right? But is this possible? No, because we can only return to a black square after an even number of moves, right? Because we need black must go to white and white must go to black. So we only have black squares if we start on black squares after an even number of moves. So we get black squares on the second move, the fourth move, and etc. And we get white squares on the first move, third move, etc. And this means that we can never reach a black square on an odd move. So another invariant is the modular invariant. On the island of Trichroma, there are 10 blue, 15 red, and 20 yellow chameleons. If two chameleons of different colors meet, they both simultaneously change to the third color. Is it possible for all the chameleons to eventually be the same color? So in invariant problems or in combinatorics problems, when we see problems that have 2 and 1, or like 2 and then they state 3 different groups where 2 can change into the last one, it's usually hinting at modulo 3. And it even says try in the name, so it wants you to use modulo 3. So we have 2 chameleons of different colors, which change to the third color. When they change to the third color, let's say we have blue and red meet. So we have B, R. We get minus 1B, minus 1R, and we also get plus 2 yellow, right? But then when we take this mod 3, this is just plus 2B, plus 2R, and plus 2 yellow. What does this mean? This means that after any like number of moves or any number of times that 2 chameleons of different colors meet, then the number of blue, red, yellow modulo 3 will be the same as they originally were. And we see that the number of blue originally was 1 modulo 3, number of red was 0 modulo 3, and number of yellow was 2 modulo 3. And we want it to have all chameleons eventually be the same color, right? What does that mean? That means we have either 45 blue, 0 red, and 0 yellow, or 0 blue, 45 red, 0 yellow, or 0 blue, 0 red, and 45 yellow. But that means we must have all of the 3 groups equivalent to 0 modulo 3, right? Because 45 is 0 modulo 3, because it's 3 times 15. 0 is 0 modulo 3, and we have 0 for the last one as well. But then we start off with 1, 0, and 2. Oh, wait, no. The modulo 3 will change by the same amount. They don't stay the same. But then if they change by the same amount, then if we have 2 being different, let's say the 1 and the 0, then they will stay different after any number of moves. And if they stay different after any number of moves, then we can never reach them all being the same, which is why we can't go to 0, 0, 0. So this is a sum invariant. We have the numbers 1 through 10 written on a whiteboard. Each turn you replace 2 numbers with their sum. After a series of moves, only 1 number is left on the blackboard. What is that number? Oh, on the whiteboard. So in this problem, we look at something, we try to find the invariant, and the invariant is something that does not change, right? And if we replace two numbers with their sum, we take a and b, and replace it with a plus b, then what does not change? The sum does not change, right? So we can extend this to all of the numbers on the whiteboard. So we can take it to the sum of all numbers, right? Because if we take a, b, then the sum of these two that we take was a plus b originally. And if we replace it with a plus b, then the new number that we replace the two numbers with will have the same sum as before, which means the whole whiteboard has the same sum as before, right? So notice the sum stays constant. And because the sum stays constant, the sum at the end will equal the sum at the beginning, right? And the sum at the beginning was just 1 plus 2 plus 3 plus 4 through 10, which is 55. And when we only have one number left on the board, then it will be the same as the beginning, which means we have 55 on the board after 9 moves. This is a modified sum. It involves a product as well. It's slightly harder. So we have the numbers 49 over 1, 49 over 2, all the way through 49 over 97 written on a blackboard. Each time we replace two numbers, a and b, with 2ab minus a minus b plus 1. After 96 times doing that action, one number will be left on the whiteboard, and we need to find all possible values for that number. So when we see these numbers where we replace two numbers with something involving a times b, then we probably need to look at the product, right? So it's probably something like a, like n times a, some number times a, and then we see minus b, right? So that probably hints to -1, and then times some number times a -1. Number times b -1, because it's symmetric for a and b in this expression. So when we see these expressions, we try to factorize them. How do we factorize 2ab minus a minus b plus 1? If we have the number in front of a and in front of b being the same, because we want an invariant that does not change no matter what number we have, then we would have to have square root of 2 to get to 2ab, right? So that will be pretty hard to deal with. So we should try to get this to a square number, because that'll be n squared times a times b, which is a term of something that looks like this. So we should try to multiply this whole expression by 2 to get to 4 times a times b, because 4 is a square number. So we get 4ab minus 2a minus 2b plus 2. And what's special about this number? This is just, what is special about this expression? This is just 2a minus 1 times 2b minus 1 plus 1, right? But then we have a plus 1, and we have minus 1s inside the brackets. Because if we take the product of 2a minus 1, so like each element, we call it a1, a2, all the way through a97. We take the product of 2a1 minus 1 times 2a2 minus 1 through to 2a97 minus 1. Then that will be an issue, right? Actually, that's not an issue, because we would have to take this expression. If we replace 2a and 2b, if we replace a and b with this expression, then we would have to perform the same operations on this expression too, right? So if we take 2a, b, if we take 2ab minus a minus b plus 1 times 2 minus 1, we get this is equal to this thing minus 1, which is also equal to 2a minus 1 times 2b minus 1. Right. So we found something that does not change. We can just take some function of 2 times some element of times each element minus 1. And then when we replace it by 2ab minus a minus b plus 1, then it will stay the same. That product will stay the same. So I mean that, where is it? We take some function f equals 2a1 minus 1 times, where a1 is like the number in the first position on our blackboard, it doesn't really matter. And then dot, 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 because we don't know how many numbers we're dealing with. But then we know that this will always stay the same, right? And because it stays the same, the value that it has at the beginning will equal the value it has at the end. And then to get the final value, because we want to look at when one number remains, that one number will be the same as this, right? The function for that one number will be the same function as for this number. And for the original condition, we have 98 over 1 times 90, oh wait, minus 1. Times 98 over 2 minus 1 times all the way to 98 over 97 minus 1. Oh, also, when we have a number that's related to another number, then we should probably like try to use that, because we know that 49 times 2 minus 1 equals 97. And it turns out that the pattern we're looking for involves something times 2 minus 1, right? So it's a pretty big hint. And then this big expression just boils down to 97 over 1 times 96 over 2 all the way to 1 over 97. And then these terms will cancel and leave us with equals 1. So we know that 2 times the final number, capital A, minus 1 equals 1. And then we can move this number to the other side, and this gives us A equals 1. So the number we'll be left with at the end will be 1. So this is another sum invariant. It's a weighted sum, I think. So we have a chessboard with 8 pawns at the bottom rank initially. Each turn, you take a pair of 2 adjacent pawns in the same rank and replace them with a single pawn directly above the left pawn of the pair. And is it possible that after some number of moves, we have 1 pawn in the last rank? So firstly, this looks like some random game that I made on a random chessboard, right? And how will this relate to sums? So in these types of problems, we try to find an invariant, but then we're not really given any numbers. So we have to assign numbers. So initially, we have, let's say, 1, 2, 3, 4, 5, 6, 7, 8. And then we take 2 and replace them with 1, right? If we take 2 and replace them with 1, what does this remind you of? It reminds you of that whiteboard problem where we take two numbers on a whiteboard and replace them with their sum, right? So if we can find something similar for our current problems, that'll be good. So the strategy to deal with this is we assign weights or values to each rank, right? The bottom rank, we can call it value 1. And to get to the next rank, we need 2 from the bottom rank, so we can call it value 2. We can say that each pawn on this rank has a weight of 2. And then the next one, we need 2 from this rank, so it has a weight of 2 to the 2. After that, it has 2 to the 3, because we need 2 from the rank before, and then dot, dot, dot. And the final one has 2 to the 7 equals 1 to 8. So we know that the total of all of these weights will stay the same, right? And initially we have 1, 1, dot, 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 all ones. So the total initially is 8. Total is equal to 8. And can this total change? No, because when we move to the next rank, we remove 2 and replace it by 1, which will preserve our total. We can take an example where we have all 8 in the bottom rank, and then we do the first move where we remove these 2 and replace it with this one. And then we still have 1, 2, 3, 4, 5, 6, 7, 8, which means the total stays at 8. But then we need the total to be 128 to be able to get to the last rank, which means this is definitely impossible. So now we move on to coloring invariance. We remove the 2 opposite corners of this chessboard. Can we tile the chessboard with 2x1 dominoes? So this problem might seem a bit hard or a bit random at first, so we should just play around with it. So let's say we remove this one and we remove this one. So what does that do to us? Does that make the board symmetrical? Well, in a sense, it's symmetrical about this line, right? But the number of whites and the number of blacks has changed. I mean, respectively, is not the same anymore. So the number of whites is now 30. And the number of black squares is now 32. It's still 32. So now we can play around with our dominoes. If we put a domino here, it takes these 2 squares. If we put a domino here, it takes these 2 squares. If we put a domino here, it takes these 2 squares. And then we realize that each domino that we put down must occupy 1 white and 1 black square, because it can't take 2 black squares since they'll look like something like this, right? So it must have 1 white and 1 black square. And to tile the whole chessboard, we'll need 31 dominoes, because each domino takes up 2 squares. So 31 dominoes, right? But then that would require 31 white squares and 31 black squares. But we have 30 white squares, which is not enough to have 31 dominoes, since each domino must occupy 1 white square, right? Which means we can't tile the chessboard anymore. So this is another chessboard coloring problem. Is it possible to make a walk around a 8x8 chessboard with squares such that you walk on each square exactly once, such that your start and end positions are in opposite corners? You are only allowed to walk to an adjacent square. Oh, someone joined. That's good. Hello, we're doing invariance. Uh, wait, what do I do? Okay. So I'll just give you a recap on what we've done so far. We did some example scenarios. It's pretty simple. And then we covered an introduction. So an invariant is basically a property or quantity that does not change, even though other things do. So if we move coins from one pile to another, the total number of coins does not change because we don't take away any coins from these two piles and we don't add any coins from somewhere else. And if we take an odd number and keep adding some even number, we will stay odd, right? And so that does not change no matter what operation we do, no matter the number of operations we do. And that's called parity because parity is odd or evenness. And then we also briefly introduce monovariance, which is just things that only change in one direction. So it's only increasing or decreasing. And invariants are things that don't change during a process. Usually these are for problems where you need to return to an original state or initial condition. But then if we have something that's always increasing or always decreasing, then obviously it can't return to the original value. So that's a pretty good way to prove it. And then we also looked at some classical invariants of parity, which is odd and evenness, or mod 2. Modular arithmetic, we covered some mod 3 sums. So we just take the total sum of all the elements presented, or weighted sums, where we assign values to some stuff, or like assign weights to some stuff. We also looked at, we just covered some coloring arguments. So this is a parity invariant. It's pretty straightforward. This is a modular invariant. So in Olympiad problems, when we see 2 and 1, or two things changing to a third thing, or we see lots of things hinting at 3 in the problem, which says, so this try, we have 3 different types of colors of chameleons, and this 2 things change to the third color. This clearly hints to us that we need to do something based on 3, right? So we look at it based on modulo 3. If we have 2 chameleons changing to the third color, we have -1 blue, -1 red, +2 yellow, let's say. Then modulo 3, this is the same thing as +2 blue, +2 red, +2 yellow, or -2 blue, -2 red, -1 yellow. Oh, I mean -1 blue, -1 red, -1 yellow. Which means that the relationship of these 3 will stay the same, like the distance apart modulo 3. So initially we have 1, 0, 2 modulo 3, right? 10 is 1, 15 is 0, and 20 is 2 modulo 3. And then we want to get to all 3 chameleons being the same color, which is 45 of one color and 0 of the rest. And we know 45 is 15 times 3, right? 15 times 3 must be 0 mod 3 because it's a direct multiple of 3. And 0 is equal to 0 mod 3. But then if we have that the relationship of the number of blue, red, and yellow modulo 3 stays the same. So if they're originally not equal, then they can't be equal, right? Because after each move, we add 2 to each number modulo 3. So it doesn't change like the distance apart. Then we can never reach 0 modulo 3, 0, 0, 0 modulo 3, which means we can never reach the same color for all types of for all chameleons. And then there's also sum invariance. So this is a basic example. We have the numbers 1 through 10 on a whiteboard, and each turn we replace 2 numbers with the sum. And after some number of moves, we have only 1 number left on the board. This number of moves will be 9, right? And then we just take A, B to become A plus B. That's basically what this problem boils down to, right? And then we look at the sum. Originally, we have A and B. The sum of A and B is A plus B. And after that, we have only A plus B, which has a sum of A plus B, which means the sum of the variables involved in our operation will be constant, right? This means the sum of all the numbers on the whiteboard will be constant. So we know that the sum of all the numbers on the whiteboard will stay the same no matter the number of operations. And this means that the sum at the beginning will equal the sum at the end. And at the end, there's only one number. At the beginning, there's 10, which is 1 through 10. So at the end, the one number left will be the sum of 1 through 10. This is a slightly harder modified sum. The motivation behind this problem is when we see A, B, A times B, we probably have to do something like n times A minus 1 times n times B minus 1. And then because 2 is annoying to deal with, if we have this scenario, we can just multiply the whole expression by 2, which gives us this number, and then it gives us this factorization. This is pretty hard to spot, so it's fine if you don't understand for now. You can look through the slides after. And then after that, we looked at a weighted sum. So in this problem, we have a chessboard with 8 pawns at the bottom rank initially. After each turn, we take a pair of 2 adjacent pawns in the same rank and replace them with a single pawn directly above the left pawn of the pair. So we take these 2, and then this one is what we have after. Wait, I think the original problem said that we can replace it with 1 pawn above any of the 2, or like 1 pawn in any position, but it doesn't matter. And then we want to have 1 pawn in the last rank. So in this problem, we actually assign no actual values, right? We just have the number of pawns at the bottom. And this means that we have to assign some weights by ourselves. And then if we look closely, to get from the bottom rank to the next rank, we need 2 to get to 1 on the next rank. So the relationship will be 2 times the bottom. So we can assign a weight of 1 to the bottom just arbitrarily, which means the weight of the next rank will be 2. And to get to this rank, to the next one, we need 2 again, right? So it'll be 2 times 2, which is 2 squared. And then repeating this process, we have 2 to the 3. And then when we get to the top, we have 2 to the 7, right? And then we know that the total weights will be the same, right? That's obvious because we can look at, say, an example scenario. We have 8 at the bottom, and then we change these 2 to this one. So originally we have 8 times 1. We change these 2 to this one. Now we have 6 times 1 plus 2 times 1, which is still 8. So our sum or total weight will stay the same at 8. But then we need a total weight of 128, right? Or like a total weight of at least 128. And because we have 8, which is much less than 128, we can never do this. And then we looked at this problem. It's a pretty classical coloring problem where we tile the chessboard with 2x1 dominoes uh, after removing 2 opposite corners. Have you seen this problem before? Can you tell me in the chat? Wait. Hmm. Just say yes or no in the chat. Okay, no response. I'll just take that as a no. So in this problem, let's just remove 2 opposite white squares, right? After removing 2 opposite white squares, we're left with 30 white squares and 32 black squares. But then if you play around with some dominoes that we drew on the whiteboard, we notice that each domino must occupy 1 white and 1 black square. Exactly 1, right? Because it can't occupy 2 black squares and it can't occupy 2 white squares. Because that would be diagonal and that just doesn't work. So to cover all 62 squares of this chessboard, because we took away 2 corners, we must have 62 divided by 2 dominoes, right? Which means we must have 31 dominoes. But then we only have 30 white squares, and each domino must occupy 30. Each domino must occupy exactly 1 white square, which means we don't have enough white squares to complete the tiling. So it just doesn't work. We can't tile the new chessboard with 2x1 dominoes. So now we're up to more coloring invariants. Is it possible to make a walk along an 8x8 board with squares such that you walk on exactly each square exactly once, such that your start and end positions are in opposite corners? You are only allowed to walk are only allowed to walk to an adjacent square each move. Can you tell me your answer? Just say yes or no. So originally, let's start at H1, and then we can move to G1, or we can move to H2. And then after that, let's say we move to H2, we can move to G2 or H3. So it's like that. Can you tell me your answer if we can move from H1 to A8 while covering each square exactly once? So if we just like do some random moves or like the obvious moves, let me just copy this chessboard. Wait, what? Why did I copy everything? Okay, if we just do some random moves, right? Let's just ignore this mess. Then we can do, let's just do this. So we started at this black square in this corner and we ended up over here. Notice that this square is not the same as this square, right? And so this movement pattern does not work. So that should probably tell us we should try out a few more movement patterns, right? But then that should give us a feeling that it doesn't work. And to prove that it doesn't work, we can use parity. So notice on the first move, from a black square, we must move to a white square, right? Because if we move from a black square to a black square, it must be diagonal, which is not directly adjacent. And from a white square, we must move to a black square, right? Because to move from a white square to a white square, it must be diagonal, which is not directly adjacent. So we know we have black to white, and we know we have white to black. And after how many moves? After 63 moves, we want to get from black, we want to get from, white, because H1, to white, which is A8. And then notice we can only achieve this by having an even number of moves, right? We start off at white, and then we must go to black, and then we must go back to white. And this is achieved after one move, two moves. So after two times k moves, where k is some whole number, we will be able to reach the same color square. And we want to reach the same color square after an odd number of moves, because to cover the whole board, we have 63 moves since we start on one of the squares originally. And 63 is an odd number, right? So we have an odd number of moves, which is not 2 times k, or which is not even. So it doesn't work. 63 odd. But we need oh, even for the same color. So this is a random observation, but have you realized that the opposite corners of a chessboard are the same color? This strategy has been used, I mean, this observation has been used 2 times so far. It's been used this one in this problem when we remove these two opposite corners, and in this problem where we try to walk across the chessboard to end up on opposite corners. So when a problem asks you to remove opposite corners of a grid or chessboard, you should probably think back to this and think of how this affects it. Like usually it just makes it asymmetrical, where we have more whites than blacks, or more blacks than whites, and then we can use that condition to do something interesting. So now we'll cover the handout problems. So consider a triangle in uh, in the lattice space with vertices. Oh, that was a badly drawn line. Is there a line tool on this? There is. Okay. What does this do? So we take a triangle situated at 0, 0, 1, 0, and 0, 1. So this is our triangle. And then we try to, each move, we can move one of the vertices along a line parallel to the other two vertices. So let's look at this vertex. Oh no, let's look at this vertex. Each move, we can move it along a line parallel to the other two vertices. What does that mean? That means we can move it along a line parallel to this, right? Which means we can move it anywhere over here. Is it possible to, after a finite number of moves, have the vertices of the triangle be at 1, 1, 3, 1, and 4, 2? This invariant is pretty difficult to spot if you haven't had any invariant practice, but I'm just using this problem to show you that there's lots of different invariants that can happen. So what thing are we looking for? In invariant problems, usually it asks, is it possible to? And sometimes it is possible to, but then you have to have like a very complex number of moves. And most times it's not possible to. And when it's not possible to, we try to use some invariants to prove that it never changes or always changes in one direction. So what does not change in our scenario? Can you tell me in the chat? Is it the side length? Is it the perimeter? Something does not change about our triangle, no matter what we do. Okay, I'll just give you a hint. So the thing that never changes is our area. The area of the triangle never changes. So we have an initial area, which never changes to our final area, right? And what's our initial area? Our initial area is, oh no. So the area of a triangle is half base times height, right? And then after each move, we get, so let's say after the first move, we have this one moves over here. What's the height? The height is this. And what's the base? The base is this. So half base times height is half of 1 times 1, which is 1/2. And then now let's look at our new triangle. Let's say this line, this vertex moves along this line. This is a pretty hard thing to see, by the way, because it's pretty counterintuitive. And then what's the base? The base is, well, this is pretty hard. So the base will be square root of 2. And then the height will be square root of 2 over 2. Or 1 over square root of 2. So our area of the triangle that we are trying to move will always stay at 1/2. But then what's the area of the triangle we're trying to get to? The area of the triangle we're trying to get to is base times height, which is 2 times 1 over 2, which is 1. And that's not equal to the area of our initial triangle. And we know that the invariant here is the area, right? It never changes. But then we have different areas of the triangle we're trying to get to in our initial triangle, which means we can never reach the triangle at 1, 1, 3, 1, and 4, 2. Oh, we're running out of time, so I'll just cover one important problem. Oh, we haven't done monovariants yet. Okay. Is this a good monovariant problem? Probably is. Okay. So we have this problem where we have several stones along an infinite strip of squares, right? We don't know the number of stones in each square, or we don't know the number of stones in the whole strip as well. We just know we have several stones. And then we want to, each move, we can pick up 2 such stones and move 1 to the preceding square and 1 to the following square. Is it possible to return to the starting configuration after a finite sequence of moves? So how does this relate to monovariants? We can see that it relates to monovariants because it asks us to prove that is it possible to return to a starting configuration, right? If it's a monovariant, then something always increases or something always decreases, which makes it impossible to return to the start. And if it is possible to return to the start, in Math Olympiad, the constructions are probably pretty hard. So this is just inspiration from being lazy, kind of. But it's also strategic. So the way to solve this is to look at this, and it moves, say we have 2 squares in the same square, and then one moves over here, 2 stones in the same square, and one moves over here. And then if we look at this from like a big perspective, what happens to the overall positions of the stones? The overall positions of the stones will actually be moving away from some central position, right? Because one of them will move out, one of them will move out as well. But then we can also have like, say there's 2 stones in here, and then the next move, we move this stone back, and then we move this stone out. But then after those 2 moves, we realize this one's moved out, this stone's moved out, and this stone stay the same. So overall, it's still just moving out. It's like spreading out, right? From the center. So to deal with this problem, we should assign weights to different like squares. We can call this central one 0. This one is 1. We can also call this one 1. This is 2. This is 3. This is 4. This is, oh, we can call this one -1 actually. -2, -3, and -4. So after each move, let's say we start at square t, right? And it moves from t, one stone moves from t to t minus 1. One stone moves from t to t plus 1. And then how do we make this always increasing or always decreasing? Obviously, we can't just take the values as given, right? Because t times 2 is 2t. And then t plus 1 plus t minus 1 is also 2t. So it just stays the same. That's not a monovariant. That's not increasing or decreasing. We want something that's always increasing or decreasing. And the answer to that is we take t squared. We take each stone's squared weight, okay? Or we can assign a weight of the number squared. So this stone has a weight of t squared. This stone has a weight of t squared. Well, it's not like its actual weight. We just assign some numerical weight. And then when it moves, this one becomes t plus 1 squared. And this one becomes t minus 1 squared, right? You'll see why this is important in a second. So now we take the total weight, let's say, of these initial and after condition. So initially, we get 2t squared, right? Because that's just t squared times 2. And then after one move, we get t plus 1 squared. And we have t minus 1 squared. Now, what is this? This is t squared plus 2t plus 1. And this is t squared minus 2t plus 1. When we add these together, we get t squared times 2. And then the plus 2t and minus 2t cancel. And then we get plus 2. So notice the total assigned weight has increased after each move because t can be any square, right? And if the total assigned weight increases, then the assigned weight can never return to the initial condition after some number of moves, right? But then we want it to return to the initial starting configuration, which must be impossible because it's always increasing. And we are done. It's that simple. You can do the rest of the problems of the handout in your spare time. This problem gives you a big hint. This is also threes, right? So what do you do? Probably use one of the strategies discussed earlier in the slides. And then for this problem, this is a pretty interesting problem. I think it's called permutation parity. So it's basically where you have some number of elements that are flipped around compared to the order of 1, 2, 3, 4, 5, 6. And then you just use that. It's like pretty, it's pretty straightforward, I think. And then, oh wait, permutation parity. You should just watch like a YouTube video or something of this. It's a pretty important strategy in Math Olympiad. And this is, you replace with AB plus A plus B. We discussed this earlier. If we have AB, it's probably something to do with the product. Also says product. And then this one, we reverse the colors inside it. It's probably very similar. Yeah, it's the same idea as this problem in the slides. this problem the sides. So I think what is it? It's the same idea as this problem, the 6x6 grid of lights. You can just search the problems up, I think. They're all available online. And then in this one, we have a table with one real number in each cell. If it's glowing, then the sum is non-negative. So for this one, uh, you try to use a monovariant because you try to improve the sum each time. But then there's only some total number of possible sums given the initial numbers. And then we'll prove that after some number of moves, we have all the rows and columns are maximized and thus will be non-negative. So this is maximizing using monovariant, which is something that only changes in one direction. Oh, you have to prove that it reaches the maximum as well. It's not difficult to prove. I won't spoil how you prove it though. Well, I think I already did, but yeah. And then this problem, you can just play around with it. I won't spoil it for you. And then this problem will be, it looks pretty hard, but when you play around with it with like smaller cases or something, it's pretty simple. Well, you don't need smaller cases to deal with it. And then for this problem, we look at the total sum that's added and the total sum that was originally there. So originally we have 1 through 2n on the whiteboard, and 2n places numbered 1 through 2n. So it can be like our 2n places are the first place, second place, all the way to our 2nth place. And then we can have like 3, 4, and then something random, and then we can have like 1. So it's like random positioning, and then we add its place to each number, and we have to prove that two numbers, like, so we get 4, 6, dot, 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 2n plus 1. Right, because we just add them. Oh, this is not a dividing sign. This is not a dividing sign. And then we need to prove that there are two numbers that's left that's equal under modulo 2n. To deal with this problem, we know that the original sum is 1 plus 2n, and the sum that's added is, we know that 1 is added, 2 is added, all the way to 2n is added. So the sum that's added is also 1 through 2n, the sum of 1 through 2n. And then we use that to deal with this problem. I think that's it. Do you have any questions? I don't think I've spoiled these problems too much, but yeah. Just tell me your questions in the chat, or you can unmute and ask. Okay, no questions? Then the session is over. Thank you for coming. Uh, wait, yeah. The class is over. You can leave now. Unless you have some other questions.